Welcome to the deep dive. If you pause right now and just take inventory of the air around you, you realize you are absolutely swimming in a dense soup of electromagnetic energy.
It's everywhere.
Yeah, we're talking 5G running at several gigahertz, Wi-Fi 7 getting ready to launch, Bluetooth meshes, industrial monitoring equipment. I mean, every device constantly battling for bandwidth.
It really is an environment of electromagnetic saturation, and this constant, almost chaotic bombardment creates a really specialized engineering problem, doesn't it?
It does.
How do we effectively shield extremely sensitive areas, think highly accurate sensor arrays, maybe secure data centers or advanced medical diagnostic suites, without resorting to building massive, rigid, and let's be honest, often impractical walls of traditional shielding material?
Right, you can't just build a lead bunker everywhere.
Exactly. We need solutions that are high-performing, ideally lighter, and potentially tunable. That's the key.
Exactly. That specialized need for efficient, localized, and crucially, tunable electromagnetic modulation is what drove scientific analyst Justin Lake to publish a conceptual paper that we found, well, truly provocative. It's titled Resonant Shielding: Conceptual Exploration of Encapsulated Lead-Based Coatings for Electromagnetic Modulation.
And what Lake is proposing here is quite interesting. It's a revisit to a material that is virtually synonymous with shielding, lead.
Right, the classic.
But he's not talking about bulk lead sheets, the kind you might imagine in an old X-ray room. He's talking about leveraging its intrinsic physical superiority, which is undeniable, but within a modern, highly engineered composite coating.
Good.
So the mission of his paper, and really our deep dive today, is to explore the theoretical framework he lays out for successfully balancing lead's superb shielding performance, which is frankly unmatched in many ways, with the absolute necessity of modern safety requirements.
And wrapping it all up in a convenient, maybe even tunable form.
Precisely. That tunability is a big part of the conceptual leap.
The core paradox, though, it hits you immediately. Lead, with its high density, high atomic number, its conductivity. It's a phenomenally effective attenuator for radiation and EM waves.
Phenomenal, no question.
But it is also notoriously toxic. I mean, there's a reason its use has been so severely restricted in most general applications, and rightfully so.
Absolutely. Health risks are paramount.
So the conceptual leap Lake attempts to make is, how do you safely harness the power of lead without incurring that unacceptable public health risk? If the theory holds, it could represent a pretty profound conceptual shift in how we approach RF shielding.
It could. So let's unpack this blueprint he's laid out.
Okay, so when most people think of lead shielding, like we said, they probably picture an X-ray technician standing behind a thick wall or maybe wearing the incredibly heavy apron during a procedure. Let's start with that legacy.
Right.
Lead, atomic number Z equals 82, density around 11.34 grams per cubic centimeter. It's been the gold standard for attenuating high-energy ionizing radiation, things like X-rays and gamma rays, for decades, medical, nuclear contexts.
And that history is vital because it confirms LEED's sort of unparalleled physical superiority when it comes to mass and blocking capacity for that kind of radiation. But the modern electromagnetic environment presents a really different challenge.
It's not just high-energy particles anymore.
Exactly. Lake emphasizes we're moving beyond just blocking, say, diagnostic X-rays in a hospital setting. We now require robust, localized electromagnetic modulation and interference control. And it's against a vast and frankly chaotic spectrum of non-ionizing radio frequency, RF, and microwave signals.
That's a really crucial distinction. You know, when you're shielding against gamma rays, you need that high density, that sheer mass, to absorb particles through atomic collisions, basically stopping them physically.
Brute force.
But when you're shielding against RF waves, which are electromagnetic fields, the primary mechanisms change completely. It shifts from bulk stopping power to things like reflection and absorption, which are driven much more by the material's electrical properties.
Precisely. Conductivity becomes king. And when Lake critiques the current alternatives, he finds they tend to fall short, often because they just cannot match that combination of high density and high conductivity that LEED inherently offers.
So what are some of those alternatives he mentions?
Well, consider typical ones like polymeric composites. These are often light and flexible, which is definitely a plus in many situations.
Sure, easier to handle.
But they are generally orders of magnitude less effective at actually attenuating high-frequency EM fields unless you make them prohibitively thick, which kind of defeats the purpose if you're trying to save space or weight.
Right. Then you have materials like tin-based coatings or some of the heavy metal oxide glasses. like specialized lead borate glasses, which have seen some use in radiation shielding.
Yes, those glasses can be effective for shielding, certainly, but they introduce massive structural limitations. They are brittle, they're rigid. You simply cannot spray a complex, multi-curved surface or line the inside of existing infrastructure conduits with a rigid sheet of glass.
Well, conformal coating there.
Not at all. So that lack of structural flexibility immediately limits their application in modern, often tight and highly variable architectural spaces or inside complex machinery.
And conceptually, he points out, they all share one major functional failing, right?
Yeah.
They generally provide very general broadband attenuation.
That's the key point. They basically knock down all frequencies across the board, more or less uniformly, like wearing sunglasses that just dim everything.
But as our device landscape gets more crowded and complicated, our needs become more surgical.
Exactly. That's the core realization driving Lake's conceptual shift. We increasingly need frequency-selective attenuation. Think of a scenario maybe where a sensitive internal sensor needs to operate cleanly at, say, 900 megahertz.
Okay.
But the structure it's in is constantly bombarded by local 5G signals at maybe 3.5 gigahertz. You don't want a shield that just blindly sacrifices the internal signal just to block the external noise.
You need a notch filter, essentially, something precise.
Precisely. You need a precision filter.
So Lake's proposition, then, is to combine LID's really phenomenal physical properties, its conductivity, its density, with modern nanoengineering techniques, things like immobilization and encapsulation. Theoretically, this combination allows us to engineer a coating that offers superior broadband shielding capability, sure, but also through the layered structure, which we'll definitely get into.
Yes, that's critical.
It allows for targeted, frequency-selective attenuation for those specific, known, troublesome RF bands.
In essence, the concept is taking the world's arguably most effective EM barrier material, miniaturizing it, locking it safely into a composite matrix, and then adding a kind of tunable dial to it.
Which sounds incredibly ambitious.
It is ambitious, and it definitely requires a deep dive into the underlying physics to see how that could even be possible.
All right, let's transition into the fundamental physics that Lake uses to really argue the case for lead, specifically in the RF spectrum. As you just mentioned, for RF shielding, electrical conductivity, that's sigma. Sigma is really the name of the game. It drives the primary mechanism of reflection.
Exactly. When an electromagnetic wave hits a good conductor like lead, its high conductivity allows currents, eddy currents, to flow very easily right on the surface.
Okay.
These induced currents then generate their own secondary electromagnetic fields, and these secondary fields largely cancel out the incident wave, effectively reflecting most of its energy away from the conductor.
So reflection is the first line of defense. But some energy still gets through, right?
Yes. The wave that isn't reflected does penetrate the material, but it gets attenuated very quickly. And that penetration depth is quantified by this really critical concept called skin depth.
Skin depth.
Yeah.
Symbolized by the Greek letter delta. Delta. For our listeners, let's really try to nail down this concept. Why is delta the absolute benchmark when you're designing an RF shield?
Well, skin depth is defined as the distance an electromagnetic wave travels inside a conductor before its power density is reduced to $1. That's 1 over the mathematical constant E of its value right at the surface.
Which works out to about 37% of its original strength, right?
Exactly, about 37%. So if your physical shield layer is, say, 3 to 5 times thicker than the calculated skin depth for a particular frequency you're worried about, you've generally achieved excellent attenuation for that frequency. The wave is effectively snuffed out.
But conversely, if your layer is significantly thinner than the skin depth,
Then the wave barely even registers the shield. It just passes right through with very little loss. So the skin depth tells you the minimum thickness you need to even start being effective.
that immediately ties the physical thickness of our proposed coating directly to the required shielding performance. And Lake's paper, of course, confirms this mathematically, showing an inverse relationship.
Yes, the relationship is driven by the formula. Delta equals the square root of 2 divided by omega times mu times sigma. That's delta Vines 2.
Okay, let's break that down. Mu omega is the angular frequency.
Which is directly related to the operating frequency of the signal you're trying to block, 5 Vines. Specifically, omega is 2 pi SAO.
Mu. Mu is the magnetic permeability of the material.
Correct. How it responds to a magnetic field.
And sigma. Sigma is the electroconductivity we just talked about.
Right. So crucially, you see that frequency term omega in the denominator under the square root.
Oh.
This equation proves mathematically that as the frequency of the incoming wave increases, the skin depth, delta, necessarily decreases.
So higher frequency waves, like microwaves, they don't penetrate conductive materials very deeply at all.
Not nearly as deep as lower frequency waves. They are stopped much closer to the surface. Their energy is dissipated in a thinner layer.
Which is actually kind of convenient for modern engineering, isn't it?
Yeah.
Since so much of our communications are constantly moving toward higher and higher frequencies, like 5G pushing into the millimeter wave bands, those are inherently easier to stop with thinner layers of conductive material.
Precisely. It works in our favor from a materials standpoint, in a way. And Lake's analysis specifically covers that crucial modern frequency range. He looks from 100 kilohertz, which captures some lower-end industrial interference, all the way up to 10 gigahertz, which covers most typical RF and microwave applications like Wi-Fi, Bluetooth, and lower 5G bands.
That's a huge spectrum, almost 5 orders of magnitude in frequency.
It is. And across this huge spectrum, his analysis reveals that for bulk lead, the skin depth varies dramatically. It goes from a few millimeters at the low end, that 100 kilohertz range,
Okay, relatively thick.
down to mere tens of microns, that's millionths of a meter, at the high 10 gigahertz end.
Wow, millimeters down to microns. That single data point alone really highlights why traditional sort of rough bulk fabrication methods just won't cut it for this kind of application, does it?
Absolutely. The shield thickness has to be exquisitely engineered and controlled, especially if you want predictable performance across that wide frequency range, or if you want to optimize for those high frequencies where you only need microns of material.
You can't just slap on a thick sheet and call it a day if you're aiming for efficiency and minimum material use.
You really can't. The need for this precision really informs the entire feasibility of the encapsulated coating concept. The idea is you don't need a massive wall of lead. You potentially need an incredibly thin, yet perfectly consistent and maybe even structured layer to effectively target specific high-frequency interference.
And this focus on material minimization is obviously critical, not just for cost and weight, but getting back to it for safety. Less lead is always better from a risk perspective.
Always.
So, okay, to simulate the performance of these potentially ultra-thin layers, Lake's theoretical analysis have to move beyond just simple single-layer skin depth calculations, right? He uses multi-layer transmission line models. Why is that necessary?
Well, simple bulk calculations like the skin depth formula implicitly assume the material is infinitely thick, or at least very thick compared to the skin depth, but in a real coating.
You have boundaries.
Exactly. You have multiple interfaces. You have the outside air hitting the polymer top coat, then the top coat interfacing with the lead composite layer. Maybe there's an intermediate dielectric layer in there interfacing with the lead layer in the top coat. And then finally, the lead layer interfacing with the substrate or the interior air.
Lots of transitions.
Every single one of those interfaces represents an impedance mismatch for the electromagnetic wave. And impedance mismatches cause reflections as well as transmission with some loss. The multi-layer transmission line model is necessary because it accurately accounts for all these complex reflections bouncing back and forth between the interfaces and the transmission losses as the wave propagates through each layer.
So it gives a much more realistic prediction of the total attenuation the entire layered system provides, compared to just looking at one layer in isolation.
Much more accurate, yes. It captures the collective behavior.
And Lake used these models, importantly, to quantify the performance difference you might get by using slightly different amounts of the active lead material. He specifically modeled layer thicknesses like 0.1 millimeters, 0.5 millimeters, and 1 millimeter.
Correct. And integrating these specific data points into the analysis is key. Looking at these relatively small increments, 0.1, 0.5, 1 mil, shows a direct functional relationship between the thickness of the active lead composite layer and the resulting attenuation performance, usually measured in decibels, dB.
Right. More dB means better shielding.
Exactly. So, for example, the model might predict that a 0.5 millimeter coating provides, say, 40 D limit of shielding at a particular frequency. Increasing that thickness to 1 millimeter might boost the shielding to maybe 60 D limit.
Which is a huge improvement in shielding power. 20 D limit is a factor of 100 in power reduction.
It is. But that significant marginal gain has to be weighed against the implications of doubling the amount of lead used, the cost, the weight, the processing complexity, and critically, the overall safety burden.
So Leak's modeling essentially provides an engineering trade-off curve. It helps engineers potentially select the minimum required amount of the lead composite to reliably hit a specific performance threshold, say 50 dBA attenuation at 5 gigahertz.
That's the goal, optimization. using just enough and no more.
However, there's a caveat, right? While these models confirm the high-level broadband attenuation capacity you'd expect from lead, Lake identifies a major technical limitation in the paper. He notes that achieving true selective filtering like knocking down only that 3.5 gigahertz signal while preserving the 900 megahertz signal requires an engineering layer that goes beyond just simple thickness variations of a uniform layer.
Absolutely. That kind of surgical frequency modulation requires much more highly engineered structures within the coating itself. We're talking about potentially embedding micro and nanoscale patterns, things like frequency selective surfaces, FSS, or specifically designed resonant structures directly into the conductive layers.
So almost like printing tiny antennas or filters directly into the coating.
That's a good way to think about it. You're essentially creating what are known as metamaterials. Materials engineered to have properties not found in naturally occurring materials, specifically tailored electromagnetic responses. This is where the concept really moves from basic material science, just making a better, safer composite, into the realm of advanced electromagnetic engineering, making a material that actively thinks about frequency.
Fascinating, but also sounds significantly more complex to manufacture reliably.
Undoubtedly, that's part of why it's still conceptual exploration at this stage.
Okay, since we're now seriously talking about the possibility of manufacturing potentially complex coatings using lead, even if only in micro thicknesses, we absolutely have to swing back hard to address the toxicity hurdle. The physics might confirm lead's stellar performance, but it's the safety assessment that ultimately determines if this concept has any legs at all.
That's arguably the most critical pivot in Lake's entire paper. Safety isn't treated as an afterthought here. It's presented as the fundamental design constraint from the beginning. The primary risk associated with lead comes from soluble lead ions, the PBO form,
Right.
which can leach out into the environment, especially via wet water or acidic contact, or critically, from the inhalation of fine lead-containing dust particles, perhaps during manufacture, installation, or if the coating degrades over time.
So how does Lake propose that we counter this? He outlines a multi-layered defense strategy, doesn't he?
He does, a defense in-depth approach. Strategy 1 is a deep dive into chemistry. It's called chemical immobilization.
Chemical immobilization. It sounds almost like we're chemically neutering the lead, making it inert.
That's actually a pretty good analogy. The core goal is to convert those potentially mobile and biologically available soluble lead ions into chemical compounds that are virtually inert and, crucially, extremely insoluble under typical environmental conditions.
How is that done chemically?
It involves techniques like chemically precipitating the lead ions into extremely insoluble lead salts. The paper mentions examples like lead sulfate, PbSO, or lead phosphate, PbPO. Yeah. Lead phosphate in particular is known to be exceptionally stable and has incredibly low solubility across a very wide pH range. It's actually sometimes used in environmental remediation of lead-contaminated soil for this very reason.
Okay, so the chemical benefit seems clear. You drastically reduce the potential for lead to dissolve and leach out, which prevents it from entering groundwater or being absorbed if ingested or inhaled. But the crucial question, does this chemical transformation compromise the electrical conductivity that we absolutely rely on for the RF shielding?
That's the elegant part of this approach, theoretically. The lead is still present within the compound as a heavy metal element, so it preserves the necessary high atomic mass and contributes to the bulk density. And critically, many of these lead salts, while much less soluble, can still maintain sufficient bulk electrical properties, particularly when integrated into a composite matrix to allow for effective reflection and absorption of EM waves.
So it keeps the necessary physical properties for shielding while effectively neutralizing the toxic leachability aspect.
That's the aim. It renders the lead component biologically inaccessible, or at least significantly less accessible, while retaining its function.
Okay, that's strategy 1. Strategy 2 pushes this safety margin even further, using advanced composite materials and the concept of molecular adsorption. This involves incorporating materials with incredibly high surface areas, like carbon nanotubes, CNTs, or perhaps graphene sheets, into the composite matrix alongside the immobilized lead compound.
Right. This is where the nanoengineering gets really sophisticated. These advanced carbon materials essentially act like hyper-efficient molecular sponges, or perhaps better termed, sequestering agents.
Sequestering agents, meaning they trap things.
Exactly. They physically bind and trap any trace amounts of lead ions that might, despite the chemical immobilization, still attempt to migrate through the composite matrix over time. Furthermore, to make them even more effective, we often need to functionalize these materials.
Okay, let's clarify functionalize. What does that mean in the context of something like a carbon nanotube?
Functionalization means chemically modifying the surface of the CNT or the graphene sheet. For instance, you might graft specific chemical groups like carboxyl groups, COH, or hydroxyl groups onto the carbon structure
Why those groups?
because these particular chemical groups have a very high affinity for binding with heavy metal ions like PBS. They effectively create tiny, tailored chemical cages or binding sites right on the surface of the nanotubes that actively capture and hold on to any stray lead ions much more strongly than the unmodified carbon would.
Ah, I see. So it's an active trapping mechanism.
Yes, it significantly enhances the ability to prevent ion migration, improving the overall stability and safety profile of the composite. And there's a bonus. The CNTs themselves are highly conductive.
Oh,
So they simultaneously act as high-speed conductive pathways throughout the composite matrix, which actually helps maintain or even enhance the overall electrical conductivity needed for superb shielding performance. You get a double benefit: enhanced safety and maintained or improved conductivity.
okay. That's clever. So we've locked the lead down chemically with immobilization. We've trapped any potential remaining stray ions physically and chemically with functionalized nanotubes. And then we come to strategy 3, external encapsulation. This sounds like the final practical line of defense, the outer shell.
It really is. This is the practical security blanket, if you will, the layer that actually interfaces with the outside world and with people. It involves applying a relatively thick, durable, non-toxic, and highly impermeable topcoat over the entire lead-containing composite layer.
What kind of materials are we talking about for this top coat?
Usually durable polymers like epoxies or polyurethanes or potentially thin ceramic coatings, depending on the application's requirements for toughness, chemical resistance, or UV stability.
And the purpose is purely physical containment.
Primarily, yes. This top layer physically prevents any direct human contact with the encapsulated lead composite underneath. It also prevents lead-containing dust from being generated or escaping due to abrasion or minor impacts. And importantly, Lake references existing commercial products like lead seal and stop and similar encapsulants used in hazardous material abatement.
Ah, so this part isn't purely theoretical. There's precedent.
Exactly. It shows that the technology for creating robust, adhesive, and long-lasting exterior containment layers specifically for lead hazards already exists and is commercially viable for safety applications. We know how to do this part.
But let me push back on that practical layer a bit. In a really harsh industrial environment, or even just over decades of building life, polymer coatings inevitably get scratched, they can crack, they might suffer from UV degradation or chemical exposure.
Yeah,
Environmental wear and tear is unavoidable, right?
that's a critical point, yes.
Yeah. So if this final crucial safety layer, the top coat, eventually fails or gets compromised, doesn't that potentially expose all those carefully engineered chemical and physical sequestration strategies underneath to the environment and potentially to users? The long-term integrity of that external coat seems absolutely paramount.
It is paramount. That is precisely the long-term maintenance challenge. And Lake implicitly addresses the need for ultra-high performance and reliability by discussing strategy 4, what he calls the theoretical frontier of single-atom immobilization.
Single-atom immobilization, that sounds extreme.
It's currently very much laboratory-level experimental work, mostly in catalysis and electronics, but it represents the ultimate conceptual goal for this kind of approach.
The ultimate goal being what exactly? Maximum safety.
Maximum material efficiency coupled with minimized risk. The idea is to anchor individual lead atoms one by one onto a stable, non-toxic substrate material.
How would that even work for shielding? You need some bulk, don't you?
Well, you still leverage the electromagnetic interaction of the heavy lead atoms electron cloud. If you could create ordered arrays of these anchored single atoms, you might achieve significant EM interaction with surprisingly little total material. The key benefit is safety. Because the lead atoms are individually anchored, and the total mass of lead used would be vanishingly small, perhaps measured in single-atom layers or sparse arrays, the potential for releasing hazardous quantities, the bulk toxicity risk, could be minimized to an almost unprecedented degree.
So it's the conceptual path towards near-zero risk lead utilization, maximizing the useful EM properties while using the absolute minimum amount of the hazardous element.
Precisely. It's looking far ahead, but it shows the trajectory of the thinking. Minimize and immobilize at the most fundamental level possible.
Okay, so summing up the safety strategies, we have chemical conversion to insoluble salts, molecular sequestration using things like functionalized CNTs, robust external encapsulation with polymer or ceramic topcoats, and then this far future theoretical goal of single atom anchoring. It sounds like a formidable four-layered defense system.
It does.
But even with all this, you noted earlier that Lake is quite rigorous in stating that the resulting system, even if perfectly executed, should only be considered risk mitigated, not truly risk-free. Why the cautious wording?
That distinction is absolutely vital, particularly for regulatory approval, liability, and just responsible engineering practice. Because lead, however well immobilized or encapsulated, remains the core functional material, there is an unavoidable, continuous, absolute requirement for stringent risk management throughout the entire life cycle of the product.
What does that entail practically?
It means proper, documented handling procedures during manufacture, installation, and especially during end-of-life decommissioning and disposal. It means implementing mandatory periodic inspection protocols to check the integrity of that crucial top coat throughout the coating's lifespan, actively looking for those inevitable scratches, cracks, or signs of degradation you mentioned earlier.
So proactive maintenance becomes part of the system. Absolutely. And it means strict adherence to all existing and future regulatory standards regarding the use of heavy metals in building materials or electronic components. The potentially superior performance comes bundled with a non-negotiable, lifelong commitment to vigilance and documented safety management. It's a trade-off. Okay, so now that we've sort of grappled with the performance drivers, conductivity, skin depth, and also the really critical safety strategies for mitigation, we can start to synthesize how Lake envisions these different elements integrating together. This happens in his conceptual layered coating architecture. This multi-layer blueprint is what he proposes enables both the improved safety profile and that crucial frequency tunability we talked about.
Right, the structure is key to the function. Let's break down the three fundamental parts he describes for this conceptual system. Because as you said, the complexity seems hidden in the interactions between those layers.
Exactly. So layer one is the active lead layer. This is the real workhorse, the primary shielding component. But remember, it's not pure lead metal. It's the composite we just discussed, the chemically immobilized lead salt, like lead phosphate, thoroughly dispersed within a matrix, potentially containing those functionalized CNTs for sequestration and conductivity enhancement.
So this layer provides the initial high level of broadband EM attenuation based primarily on its effective conductivity and density.
Correct. It does the heavy lifting for general shielding across a wide frequency range. Then layer two is the intermediate dielectric layer. Now, Lake notes this layer is often optional depending on the application.
But crucial for tuning.
But, as he argues, it's potentially the key component for achieving that desired frequency modulation or filtering effect. This would likely be a thin layer of a material chosen specifically for its dielectric properties, its permittivity and loss tangent at the frequencies of interest. Think of a specialized polymer, maybe a ceramic-infused resin, something with controllable electrical characteristics.
Okay, active layer, dielectric layer, and layer three.
Layer 3 is the protective top coat. This is a layer we spent a lot of time on in the safety discussion. It's that outermost, durable, impermeable, non-toxic barrier, the epoxy or polyurethane layer that provides mechanical durability against scratches and wear, seals everything in, and shields human contact from the lead composite layer underneath.
Got it. Active core, tunable dielectric middle, protective outer shell. Let's focus back on layer two, that intermediate dielectric layer. You said this is where the system potentially transforms from being just a simple, effective broadband shield into something more like a smart, tunable filter. How does manipulating dielectric constants actually achieve frequency selectivity? It sounds complex.
It relies on wave interference phenomena. When an electromagnetic wave is traveling through the air or whatever medium is outside, and it hits the outer surface of layer 3, the top coat, some reflects, some transmits. The transmitted part goes through layer 3, then hits the interface with layer 2, the dielectric. Again, some reflects, some transmits. Then it hits layer 1, the lead composite, and again, reflection and transmission absorption occurs.
So you get waves bouncing back and forth between these layers.
Precisely. You get multiple reflections happening at each interface. Now, the amount of reflection versus transmission at each boundary depends on the impedance mismatch between the two materials. And the impedance of the dielectric layer, layer 2, is determined primarily by its dielectric constant, or permittivity epsilon, and its magnetic permeability, usually close to air, approx the prog, as well as its thickness.
Okay.
By precisely choosing the thickness and the dielectric constant of layer 2, engineers can control the phase of the wave that gets reflected back from the layer 2, layer 1 interface towards the incoming wave.
The phase relationship is key.
It is. You can design layer 2 such that for a specific target frequency you want to block, like that 3.5 gigahertz signal, the wave reflected from the lead layer travels back through the dielectric, experiences a particular phase shift, and emerges back towards the top coat exactly out of phase with the incoming wave at that frequency. This leads to destructive interference, significantly canceling out and attenuating that specific frequency.
So if the incoming 3.5 gigahertz wave is hitting the structure, you can design layer 2 to essentially bounce back a reflection that cancels out the original wave at that frequency, while hopefully having minimal or maybe just a different phase impact on the 900 megahertz signal that you actually want to pass through relatively unaffected.
That's exactly the principle. It's akin to how anti-reflection coatings on eyeglasses work, but engineered for specific RF frequencies and potentially much higher attenuation levels. This selective interference allows for the visualization, in theory, of that frequency-dependent attenuation curve that Lake discusses.
Right, the performance graph.
His modeling aims to show how, by carefully adjusting the properties, thickness dielectric constant of layer 2, you could intentionally introduce sharp peaks or notches of very high attenuation, maybe 50 or 60 dLps precisely at 3.5 gigahertz, while the attenuation down at 900 megahertz remains relatively low, perhaps only a few dB.
Allowing that internal sensor to function unhindered by the external noise source.
Exactly. That theoretical attenuation curve showing sharp dips at targeted frequencies is the conceptual proof that this layered architecture could provide localized, advanced EM modulation, not just generic broadband suppression like a simple sheet of metal.
This really does move the technology conceptually entirely out of the realm of just passive blocking and into something more like active frequency management using passive structures.
Okay, but considering this added complexity, the precision needed, and the inherent toxicity risk we keep coming back to, why should we seriously pursue this concept over existing, maybe seemingly safer alternatives? Lake must make a pretty strong case for the comparative advantages, right?
He does. He synthesizes his argument based on a combination of practical, physical, and performance metrics, where he believes this concept could potentially excel, assuming the safety hurdles can be reliably overcome. The first key advantage he highlights is mechanical flexibility.
Compared to what? Compared to existing high-performance shields, like those rigid lead-infused glass panels we mentioned, or thick, heavy aluminum or steel enclosures, these simply cannot conform to complex shapes. Lake's system, being a coating, can theoretically be applied seamlessly to irregular surfaces wrapping around existing pipes, conforming to the curves of complex equipment housings, or being applied directly to existing facility walls without requiring expensive demolition or custom rigid fabrication.
Okay, flexibility is a big plus. What's next?
Second, he argues for potentially superior durability, particularly compared to some other composite shielding approaches. While basic polymer composites filled with metal flakes might also be flexible, they often lack long-term stability. The metallic fillers can sometimes migrate, clump, or even leach out, and the polymer matrix itself can degrade relatively quickly under harsh conditions, compromising the shielding.
Whereas Lake's approach.
Lake argues that the combination of chemically immobilizing the lead into stable compounds, sequestering stray ions with CNTs, and then sealing it all under a robust external encapsulation layer should, in theory, ensure significantly greater longevity and substantially reduce the degradation and leaching risks inherent in less stable composite formulations.
Assuming that top coat holds up, of course.
Assuming the whole system holds up, yes. The third advantage is sheer practicality in many installation scenarios. Imagine, as he suggests, trying to retrofit heavy prefabricated metal or specialized glass shielding panels into a tight operational space like an existing server room or a hospital imaging suite.
Logistical nightmare.
Huge logistical effort, potential downtime, high installation costs. Coatings, fundamentally, are often easier, faster, and potentially cheaper to install and maintain in existing structures compared to maneuvering and fitting heavy, rigid structures.
Okay, those are compelling practical points. Let's try to make this concrete using the metrics from the comparative shielding table that Lake presents conceptually. This helps put that performance for vigilance trade-off into stark relief against standard alternatives. Let's compare it again to traditional lead glass and maybe a generic polymer metal composite shield.
Okay, if we evaluate based on the key metrics Lake likely considered, the encapsulated lead composite coating concept really stands out in certain areas. First, Density. Lead itself is exceptionally high at 11.34 gc-meter turbine. Even as a composite, it would likely retain a significantly higher density than polymer composites filled with lighter metals or carbon, translating into powerful attenuation capacity per unit thickness.
Conductivity.
Conductivity. Lead is highly conductive, which is essential for efficient RF reflection. The CNTs could further enhance this in the composite. Polymer composites rely on the conductivity of their filler, which varies widely but is often less than bulk lead. Lead glass has poor conductivity.
Attenuation performance.
Attenuation, dB. As we've discussed, the theoretical performance for the lead composite is potentially superior, offering high broadband attenuation plus the unique advantage of frequency tunability via the layered architecture. Neither traditional lead glass, broadband absorption scattering, nor standard polymer composites, generally lower broadband attenuation, no inherent tunability, can typically match that combination.
Okay, but now the downsides. Flexibility.
Flexibility. Here the coating concept scores high. It's designed to be conformal. Polymer composites can also be flexible. Rigid lead glass, however, scores critically low. It offers virtually no flexibility.
And the big one, toxicity risk.
Toxicity risk. This is where the balance shifts. Polymer composites, especially those using carbon or less toxic metals, generally have a lower inherent risk profile. Lead glass, while containing lead, is often considered relatively stable, though edge leaching or breakage can be concerns. The encapsulated lead coating concept, however, must be categorized honestly as risk mitigated. The inherent hazard of lead is still present, requiring that perpetual vigilance.
So that really is the crux of the entire argument, isn't it? You are potentially gaining dramatically superior frequency-aware shielding performance delivered in a thin, flexible, practical form factor.
Right.
But in exchange, you are accepting a permanent, non-negotiable need for strict regulatory oversight, rigorous quality control in manufacturing, and ongoing inspection and maintenance vigilance throughout the product's lifecycle.
Precisely. The entire feasibility of Lake's conceptual paper really rests on proving, through future experiments, that the proposed mitigation strategies, the conversion to PBSO or PE, the CNT sequestration, and crucially the long-term integrity of that top coat are robust and reliable enough in the real world to make the inherent risk acceptable for the critical high-performance applications where this might be needed.
Because, as we keep saying, if that final polymer layer fails 10 years down the line due to unforeseen environmental stress, well, the toxicity clock potentially starts ticking again. The whole long-term engineering challenge, therefore, seems to shift almost entirely from just shielding physics to the science of long-term polymer durability and the implementation of foolproof maintenance and inspection frameworks.
That's a very accurate summary of the challenge ahead, should this concept move towards reality. Hashtag outro.
Well, this conceptual exploration by Justin Lake is certainly a fascinating look into pushing the boundaries of material science for electromagnetic control. It really reaffirms that the fundamental physical properties of lead are, in many ways, uniquely suited for tackling the complexity of the modern RF challenge. The paper, I think, achieves two main conceptual feats. First, it maps out a plausible theoretical path toward achieving highly effective, thin, and potentially frequency-tunable EM shielding. Second, and just as importantly, it proposes a robust, multi-layered defensive strategy for mitigating the inherent toxicity risk, primarily through chemical immobilization and secure external encapsulation.
And crucially, Lake is very clear in his writing. This work is purely exploratory at this stage. It's a conceptual framework. The paper rightly concludes with an imperative. Before this concept moves anywhere near actual product development or commercialization, rigorous experimental validation must occur. The theory seems sound on paper, but we absolutely need engineers in the lab actually building and testing prototypes to confirm these hypotheses.
So what would be the absolute non-negotiable next steps for that experimental validation process? What needs to be proven?
Lake implies, and standard practice dictates, at least three critical areas. First is EM measurement. You need to physically fabricate prototype layered coatings based on the design principles and test them in a controlled anechoic chamber environment. You need to measure their actual shielding effectiveness across that wide 100 kilohertz to 10 gigahertz range and see if those theoretical attenuation curves specifically, that desirable frequency selective suppression, the notches actually materialize in practice and match the models.
So does the physics actually work in a real material?
Exactly. Second, rigorous aging studies. You have to subject these encapsulated coatings to accelerated aging protocols. Simulate long-term exposure to UV light, temperature cycles, humidity, chemical chemical fumes, maybe even physical abrasion, to verify the long-term durability and stability of the entire encapsulation system. You need data on how long that critical polymer topcoat can realistically be expected to maintain its integrity under various real-world stress conditions and identify potential failure modes.
Testing for those inevitable cracks and scratches we worried about.
Precisely. And third, comprehensive safety assessment. This involves detailed scientific testing to verify the actual reduction in lead leachability achieved by the chemical immobilization techniques, like the phosphate conversion, under various simulated environmental conditions, including things like acidic exposure simulating acid rain, perhaps. You need hard data confirming that the lead stays locked in place even if the outer layer gets breached.
Okay, EM performance, long-term durability, and verified leachability reduction. If, and it's a big if, these experiments manage to prove the theory viable across all three fronts, well, it could fundamentally change how we think about designing protected spaces, maybe even embedding shielding directly into devices themselves.
It really could. And it raises a powerful final question, perhaps, for you, the listener, to consider about the future of our built environment and technology. If this conceptual layered architecture can eventually provide thin, highly efficient, and frequency-tunable EM performance using a material like lead, which was previously considered almost entirely off-limits for widespread use due to toxicity, what does that imply for future shielding design?
Hmm.
We might genuinely move away, in certain critical applications, from the default of just building generic thick walls of passive metal and towards deploying highly specialized, maintenance-aware, frequency-aware protective coatings, coatings that could be embedded directly into the structure of buildings, integrated into equipment enclosures, or even applied to personal devices, capable of surgically filtering out the exact noise profiles generated by dense deployments of 6G, 7G, and whatever future wireless standards emerge.
That shift from just generic blocking to targeted surgical frequency filtering.
That conceptual shift, enabled by potentially revisiting and safely harnessing a problematic material like lead through advanced engineering, is perhaps the key knowledge we can take forward from Lake's exploration today. It opens up new possibilities, but with significant responsibilities attached.